Okay, let's do problem number 1. So I launch a projectile at a speed of 7 meters per second and an angle of 30 degrees. So I think it's always nice to draw a little picture. So this is 30 degrees, and I'm launching it at 7 meters per second. And if we're launching it in outer space, it would just keep going this direction forever. And if we were launching it in a place where there's gravity, then gravity would start to take over and it would make some type of parabolic path. Our question is, how fast is it moving horizontally and how fast vertically, at least initially? So this is just triangle trig. I know that this length is 7 meters per second because that's its overall speed. So if I want to know its horizontal component, it'll be this, and if I want to know its vertical component, it will be that. So that's just 7 times cosine of 30 degrees is its horizontal speed. The vertical speed will be 7 times sine of 30 degrees. And you should know what sine and cosine of 30 degrees are. So cosine of 30 degrees is root 3 over 2. So that means 7 root 3 over 2. And and sine of 30 degrees is 1/2. So this will be 7/2. And the units would still be in whatever units the original speed was, so meters per second. Okay, question 2. On a planet, once upon a time, on a planet without gravity, I'm on a train that's moving 10 meters per second horizontally. Okay, so here's my train, and it's moving this way at 10 meters per second. And I toss a ball straight up at 2 meters per second. So I toss a ball straight up this way, 2 meters per second. Because there's no gravity, it continues to move upward, but it also continues to move at the train's speed. So if you can imagine this, the train is moving at a pretty good clip this direction. If I toss the ball straight up, it's going to be moving, like the ball is going to be moving out this way. Because imagine it, like after 1 second, the train's moved 10 meters this way, and the ball's moved up by 2 meters. And then after another second, because the ball is continuing at the same speed that the train was moving at, because we tossed it up while the train was moving, the ball is continuing to move 10 meters per second this way, and it's also continuing to go up at 2 meters per second. So it's going to be a line kind of that looks like this. So we want a vector equation that expresses that motion. This is 10 and 2. And we're assuming, at least for part A, that this point right here counts as 0, 0. Because remember, in real life, you're allowed to define anywhere you want to be the origin of your coordinate system. So it seems like I want to express the equation of a line that moves like this. So let's see here. Let's call this position as a function of time. And I already know the speed. It's over by 10, up by 2 as a function of time. And I believe that that's it. Because each time t goes up by 1, I'm going an additional 10 and 2. So it's expressing the correct speed there. Okay, for part B, what if it leaves my hand at a different place? So I'm just going to keep the same picture, but I'm going to draw a new origin. So what if the origin now is like somewhere down here, and this distance is, what does it say in the problem? This distance is 25, and this distance is 10. And then same thing, this point is the point where it leaves my hand. So here I've got, it's like a space train, right? It's like floating in the air this direction maybe. So in that case, all we've got to do is add this initial position vector. So I'm going to define a new one where I start at 25, 10, and then on top of that, I add a line in the direction that I want to be going. Cool. So that's part A and part B. All right, what about this shape? So I hope you remember your parametrics. So it seems like I'm starting at 3, 3. So let's draw a little sketch here. So I'm starting at 3, 3. And then if it was just cosine and sine, that would be tracing out a unit circle that's centered at 3, 3. But here I've scaled the vertical dimension by 6. So that means imagine like what's the smallest and what's the largest thing cosine here could ever be. So -1 and 1. So that means that the x-coordinates range from 3 minus 1 to 3 plus 1. So that's giving me my sort of minor radius. But then the largest thing this could ever be is 6, and the smallest thing is -6. So if it's -6, that would be 3 minus 6, goes all the way down to -3, way down here. And then 3 plus 6 is going to be way up here somewhere. So it's a very tall, thin ellipse. It looks like that. Okay, so part B is asking what? It's asking, let's approximate the object's speed at time equals 1. Okay, so if you imagine plugging in t equals 1, it's like finding the point that's at an angle that's 1 radian. So pi over 2 radians is like 1.5 something, 1.57. So 1 radian is going to be, I don't know, somewhere like here-ish. So if I'm sort of imagining the direction it's moving in, right at that moment it's moving kind of in this direction. So the speed would be the length of that. But we don't really have a good way of calculating that. Once you get to calculus, that's like one of the kind of main things you're going to do in calculus. But we can approximate its speed right at that moment by looking, like, where is it at t equals 1? And then where is it just like a half, like a half millisecond later, just like a little tiny bit later. Because remember, speed is change in distance divided by change in time. So if I want to know how fast is this going right at that instant, I can just look at a little tiny change in time and a little tiny change in distance. So let's work this out. So time equals 1, and we're going to approximate this with a calculator. Give me just a second here. So at time equals 1, we are going to get 3.5403 and 8.0488. Okay, so now let's calculate, what did I say? 1.01, I think? Yes. Okay, so now let's find where is it 1/100th of a second later. Okay, so 1/100th of a second later, and it hasn't moved very much. So let's like zoom way in on what it looks like there. So what it looks like there is I've got like this part of the ellipse, and this is at t equals 1, and then like a little bit later I'm here. So the difference between the x's describes that, and the difference between the y's describes that. And so if I want to know how far did it go from here to here, I'm going to use the Pythagorean theorem to find that. So I'm ignoring the signs here. I'm just interested in the magnitude of the difference, because I want to know just how long is that delta x and how long is that delta y. So I've subtracted the two and taken the absolute values, and now we can find the distance using the Pythagorean theorem. So it's going to be square root delta x squared plus delta y squared. And on the calculator, it's telling me this number, 0.033268. So that's the distance, and the time it took was 1/100th of a second. So this is in meters maybe, and I'm going to divide it by 0.01, and so that's going to give me an overall speed of about 3.3 meters per second. Okay, what about the direction it's headed in? So the direction it's headed in would be, like I said, kind of this way. So if I do the arctangent of delta y divided by delta x, that will be this angle. But what I really want to know is this angle here. So that's going to be like pi radians minus that angle should give me this angle that I care about. So let's figure it out. So I worked it out on the calculator, and if I have pi radians minus the arctangent of delta y divided by delta x, I get 1.826 radians, and then if I convert to degrees, that is 104.63 degrees. And just a quick sanity check, like 90 degrees would be straight up, and it definitely seems like that is like a little bit past 90 degrees. So that seems like it's at least in the ballpark. Okay, so in the last problem, I've got a delicious donut here, Wow, that looks like a donut. I've got a delicious donut that is mysteriously traversing this path, and I've got a robot dog, and I'm going to send it to grab the donut. My robot dog at t equals 0 starts here, and the donut at t equals 0 starts here. And I need to choose a path so that the dog definitely intercepts the donut. So the problem here is as it's moving, the donut's also moving. So I think I have to backwards plan. I have to figure out a time where I definitely know where the donut is, and then figure out kind of how can I make a straight path to there. So let's pretend I want to have the dog intercept the donut whenever it's made a half circle and ended up here. So what time does that happen at? Well, clearly that happens at an angle of pi. And if you remember, my original equation here was 3 plus cosine t and 3 plus 6 sine of t. So t is acting like the angle. So if I want it to be at this angle of pi, that's time equals pi seconds. So I know that at time equals pi seconds, the donut is at where? It's at, let's see, 2, 3. Okay, great. So now all I need to do is I need to figure out like what's the equation for this line, and I have to make sure that at time equals pi, the robot dog is actually there. So I know the general slope of this thing. It's got a y-intercept of 0, and it's got a slope of, let's see, 3 halves. Yep, that makes sense. So one thing the equation could look like, which is not quite right, would be this. I go over 2 and up 3. This isn't quite right, though, because here if I plug in t equals 1 second, the robot dog ends up here at 2, 3. And I want that to be true at pi seconds. So it's that thing that we did before. It's like I need to figure out what's a scale factor I can multiply here so that when time equals pi, I've only gone over 2 and up 3. Well, if time equals pi, and I have a mystery scale factor, and I want to end up at 2, 3, then pretty clearly I need to multiply by something that cancels out with pi, because I need this to just be 2, 3. So my mysterious scale factor can be 1 over pi. So that gives me my final equation is going to be 1 over pi times t times 2 comma 3. Ta-da! And that's not, of course, the only equation you could have done. You could decide that you want the robot dog to intercept the donut way down here. So you could draw the equation of another line here, and then the time down here would be at 3 pi over 2. So similar thing, you'll have an equation where you give it the horizontal and vertical components, but then you scale it correctly so that at exactly 3 pi over 2 seconds, it's hit the right spot.